Good morning. This is Professor Jitendra Kumar and I am delivering second lecture of material science. In previous section we have defined phase diagram, degree of freedom, Gibbs phase rule and types of phase diagram. Now in this section we will discuss binary phase diagram. As its name suggests, binary phase diagram, that means in binary phase diagram the number of composition will be 2. Basically binary phase diagram classified into 3 different types. In first type, materials which are completely soluble in liquid as well as solid states. In the first types of phase diagram, since the number of composition is 2, therefore these materials, whatever materials there are 2 compositions, so both materials will be completely soluble in liquid states and solid states. In both states these materials are soluble. Okay, so this is the first types of binary phase diagram. Okay, this is the one of the best example of this type 1. This is copper nickel. That means copper and nickel both are completely soluble in liquid as well as solid state. Okay, so this copper nickel is the one of the example of these types of binary phase diagram. That means in both liquid and solid states these materials will be soluble. Okay, so now let us see the description of this one, this phase diagram of this copper nickel. So this is the phase diagram of copper nickel. So in this phase diagram, first of all I'm explaining this phase diagram in brief. Okay, on this axis, okay, this is the horizontal axis, okay, and these 2 vertical axes are there. Okay, these 2 vertical axes are there. So in this horizontal axis, at this point there will be 100% of copper and 0% of nickel. Okay, at this point, this is the beginning point. Okay, at this point this copper will be 100% and nickel will be 0%. As we move from left to right, percentage of copper decreases and percentage of nickel increases in composition. Okay, so suppose that, let us this point, at this point the percentage of nickel is 15%. That means percentage of copper will be 85%. Okay, so therefore as we move from left to right, percentage of copper decreases and percentage of nickel increases, but the addition of both compositions should be equal to 100%. Okay, so at this point this 50% of nickel is there, that means 85% of copper will be there, so that the composition of this one is 100%. Okay, just at point this one, let us suppose that at this point 95% of nickel is there in this mixture. 95% of nickel will be there. In that means there will be 5% of copper. Okay, so what we are observing here, at this point this percentage of copper is 100% and percentage of nickel is 0%. As you move from left to right, the percentage of copper decreases and percentage of nickel increases. Therefore at this point, percentage of nickel will be 100% and percentage of copper will be 0%. Okay, so from left to right, percentage of copper decreases and percentage of nickel increases, and at this point percentage of copper is 100% and percentage of nickel is 0%, and at this point percentage of nickel, since this percentage of nickel increases, So finally at this point percentage of nickel is 100% and percentage of copper is will of course this will be 0%. Okay, this is the first thing we have to understand, how this percentage of copper and nickel varies on this horizontal axis. Okay, now we are moving on this axis. Since at this point this percentage of copper is 100%, so this is the melting point of copper. Melting point of copper is around 1100 degrees centigrade. Similarly at this point this is nickel. Okay, so 100% nickel, so 1452 degrees centigrade is the melting point of nickel. So just you need to remember this one. The melting point of copper is 1100 degrees centigrade and melting point of nickel is 1452 degrees centigrade. Okay, this is the melting point of copper and nickel respectively. Okay, right, this is the second point we have to understand. Okay, third point, this is the phase diagram of this copper nickel alloy. Right, this is the phase diagram of copper nickel alloys. Right, since this is the melting point of copper, this is melting point nickel, so above this curve, above this curve, this mixture, this composition will be completely liquid form. This mixture, this alloy will be in liquid form. Okay, within this curve, this composition, the alloy will be in the mixture of liquid and solid. Okay, within this curve, and below this curve, this alloy will be in solid form. Right, so in this region the alloy will be in liquid form. In this section the alloy will be in the mixture of liquid and solid, and in this section is below this curve, alloy will be in solid form. So there are three different form of alloys: liquid form, this liquid and solid form. This is called messy zone. Okay, this messy zone is the mixture of liquid and solid, and this one is solid forms. Okay, so just I'm here, just you can see that this liquiders words used here, liquiders is written. So liquiders, this line is called liquiders. That means liquiders is the separators. Liquiders is the line which separates liquid zone and messy zone. Liquiders. What is liquiders? Liquiders is the line. This is the line which separates liquid zone from messy zone. Okay, this is called liquiders. That means the lines which separates liquid zone and messy zone is called liquiders. Right, this is soliders. That means this line separates messy zone from solid phase. Okay, this solid phase from messy zone. This is soliders. That means the soliders separates messy zone and alpha. This is solid. Okay, the solid phase is represented by alpha. Liquid phase is represented by L. Okay, this liquid phase is represented by L and solid phase is represented by alpha. So therefore this is liquid zone, this is liquid plus alpha zone, that is liquid plus solid zone. This is called messy zone and this is solid zone. So liquider separates liquid from the messy zone. The solider separates solid from messy zones. This is third important point we need to understand. Okay, so now just let us consider that this is CO percent of nickel. That means since percentage of nickel increases from left to right, at this point percentage of nickel is 0%. From as you move left, the percentage of nickel increases. Let us suppose this is the line, this is the point where percentage of nickel is 0%. Okay, this is the arbitrary point. Just I am discussing what is the phase at different temperature. Okay, so for just I am studying at this point. Okay, this I want to take a study the behavior of this phase and for CO percent of nickel. Okay, so just we have to draw a vertical line. This is vertical lines on at this point. This percentage of nickel is CO percent, right? So let us suppose just to start from this peak point. Okay, this is the peak point of this line. Okay, so at this point, since this point lies in liquid zone, so at this temperature, okay, at this temperature, this temperature will be greater than that of 1450 degrees centigrade. So whatever temperature is this, at this temperature this alloy will be in liquid form, because this point lies in liquid region. Okay, and we move downward. This, let us suppose that at point B. Okay, so in this zone, this alloy will be liquid form. As this point touches this curve, and below this point, liquid crystallines, this formation of solid starts. And let us put at point B, since it is in mushy zone, so there will be combination of liquid and solid zone. At point B, there will be combination of liquid and solid zone. This is liquid plus alpha. This is point B. Okay, so first of all, now we have to find, say this is the combination of liquid and solid. Okay, now we need to find how much percentage of liquid and how much percentage of solid will be there. We have to find the mass fraction of liquid and mass fraction of solid. This is our first target, because this is the combination of liquid and solid, liquid and alpha. So we need to find the mass fraction of liquid and mass fraction of solid. This is my first target. Okay, just at this point, and in liquid, let us suppose in liquid there may be some fixed percentage of nickel. Similarly, in solid phase there will be some different percentage of nickel, because this is the combination of liquid and solid phase. So in this liquid phase, there, let us suppose here 15% of nickel is there in liquid phase. So this is percentage of nickel in liquid phase is denoted by Cl. This is Cl. What is Cl? Cl is percentage of nickel in liquid phase. This L for liquid. Okay, so this Cl is percentage of nickel in liquid phase. For example, at this point, since this is the combination of liquid and solid, therefore at this point this Cl is 50%. Okay, so Cl is percentage of nickel in liquid phase. Similarly, this is alpha in the solid phase. Let us suppose 95% nickel is there. That means this is called Cs. This is Cs is percentage of nickel in solid phase. So we need to understand what is Cl and Cs. Since at point B this is combination of liquid and solid, therefore in liquid there will be some fixed percentage of nickel. This fixed percentage is Cl. Therefore Cl is percentage of nickel in liquid phase and Cs is percentage of nickel in solid phase. So we need to understand this one. Okay, this is the next point we have to be careful. ml ms, this mass fraction of liquid, and ms is the mass fraction of solid. It is clear, because this at point B there is a combination of liquid and solid, so there will be some fixed mass fraction of liquid and there will be some fixed mass fraction of solid. This is ml plus ms. ml will be mass fraction of solid and ms will be mass fraction of solid. Okay, ml and ms, L for liquid, S for solid. This is the next point we have to understand, right? Now we have to find, first of all we need to find mass fraction of liquid at point B. Okay, now we have to draw a horizontal line. Just draw a horizontal line. This A, B, C is the horizontal line. This is the line which passes through B. If horizontal line is drawn, this line cuts liquiders at point A. This same line cuts soliders at point C. This is the important observation we have to be careful. This horizontal line cuts liquiders at point A and this horizontal line cuts soliders at point C. Okay, so now we have to draw a vertical line. At both points we have to draw a vertical line. As we draw these vertical lines, just find where this line intersects on this axis. Suppose that this line intersects at this point. That means since this line cuts the liquiders, and this liquiders, if draw the vertical line, this point cuts here, so we have to find how much percentage of nickel is there. That means if here is 15% is there, that means in liquiders, in liquid phase, the 15% of nickel will be there. There will be 15% of nickel in liquid part. Why liquid part? Because this horizontal line cuts the liquiders. Therefore, and this, as you draw the vertical lines, this line cuts here, and at this point the 15% of nickel is there. That means if 15% nickel will be there, that means 85% copper will be there. So since this is, we know what is Cl, percentage of nickel in liquid line, and this line cuts liquiders, and if you draw the vertical lines, this is 15%. Okay, so the percentage of nickel in liquid phase will be 15%. Okay, now we have to we have drawn this horizontal line. This line cuts soliders. That means if you draw this vertical line, this line cuts here at 95% of nickel. That means in solid phase, in alpha, 95% of nickel will be there. This 95% of nickel will be there. Okay, this is the important thing. So we have to understand careful what is the value of Cl and Cs. So Cl is the percentage of nickel in liquid phase. This horizontal line cuts meets at point A, which liquiders. That means at liquiders, as you draw this vertical line, the line meets here, and at this point this 15% of nickel is there. Therefore, in liquid phase, 15% of nickel will be there. That means the Cl will be 15% for this sample. That means in this sample, since this is a combination of liquid and solid, so in this sample, the liquid phase contains 15% nickel. And just same process we have to follow. This line drawn cuts at point C, which is soliders line, and we have drawn this vertical. The vertical line cuts at this point, and at this point this 95% nickel is there. That means this is Cs, this percentage of nickel in solid phase. That means in solid phase, this percentage of nickel is 95%. Okay, this is the another point. Okay, we have to understand. So this is, now I am going to define lever arm rule. So first, before deriving the lever arm rule, just we have to understand some basic relationship. We need to be careful. This is very easy and interesting. So what is ml? Ml is the mass fraction of liquid, and ms is the mass fraction of solid. So if you add both one, ml and ms, it will be equal to 1. So this here, look, ml plus ms is equal to 1, where ml is the mass fraction of liquid and ms is the mass fraction of solid. This is equal to 1. And next important equation is ml into Cl plus ms into Cs is equal to 0%. What is ml? ml is the mass fraction of liquid, Cl percentage of nickel in liquid, ms mass fraction of solid, this is alpha, and Cs percentage of nickel in solid phase. This is equal to 0%. This is 0%. If whatever the mass fraction of liquid and solid to there, if you multiply this ml to this Cl and ms to Cs, if you add both one, we will get this 0%. Whatever percentage of nickel is there, we will get this one. Okay, this both equation is called governing equation of lever arm rule. Clear? This both equation is known as governing equation of lever arm rule. Right? Now we just proceed further. Next, very important point is there, because ML and MS is equal to 1. So first of all, we have to find what is the value of ML and MS, because the CL and CS can be found out from this graph, but ML and MS is still we have to find. So for finding ML plus MS, just this is ML because at point B it is combination of liquid and solid. So we have to find this ML and MS, right? So now just we have drawn this horizontal line. This horizontal line, this cuts liquiders at point A and cuts soliders at point C. Okay. Now we have to find ML. So let us suppose this is the horizontal line ABC. Okay. Now we have to find ML. Okay. Mass fraction of liquid. Since this mass fraction of liquid, this liquiders is there, so there are two segments, AB and BC. This line is divided into two segments, AB and BC. So we have to find mass fraction of liquid. So in this form, just we have to take this. Since this is liquiders phase, this is the liquiders line. We have to take the length of this one, BC, just opposite. I have to find mass fraction of liquid. So in that case, for the mass fraction of liquid, we have to take the length of this one, BC. We have to take length of BC divided total length, AC. So the mass fraction of liquid is equal to BC by AC. Similarly, the mass fraction of solid, that means this is soliders. So we have to take opposite length of opposite section. This is AB. Okay, this AB by AC. AB by AC. This is mass fraction of solid. So this is very important equation. This important equation is known as lever arm. This is just like lever arm. You know what is a lever arm? Arm. This arm is there. This is called. This is complete. This is the arm. Okay. This is the arm. Okay. And this one is the lever. So in this case, for any composition, suppose just I will discuss later on for different composition. For any composition, let us suppose this is at point B. At point B, we have to find the mass fraction of liquid and mass fraction of solid. So at any point, suppose this is point B in this situation. In this case, in this case, we have to find the ML and MS at point B. So simply we have to draw a horizontal line. We have to see whether this line cuts liquiders and soliders. This line cuts liquiders at point A and soliders at point C. So this is the total. This total length of line is AC. Okay. Now we have to find mass fraction of liquid. The mass fraction of liquid means this is liquiders. Okay, liquiders line. So if I have to find mass fraction of liquid, that means we have to take length of opposite section. This is BC. Okay, length of BC divided length of AC. Similarly, in the case of if I am to find mass fraction of solid, that means we have to take length of this section, not this section, this opposite side, because this is liquiders point. So we have to take length of this section, AB by AC. So this is all about the lever arm rule, right? So we have to be careful. So this is very important and interesting. Suppose that if you move slightly down at this point, suppose at this one, at this point. So in this case, what will happen if you draw the horizontal line? So in this case, what will happen? This point A shifts at here, and point C shifts at here. Okay, let us suppose just we are considering at this point. Okay, so we have to draw, just as you draw horizontal line, the horizontal line meets at point, cuts the liquiders at here, and this horizontal line cuts the soliders at here. Okay, now we have to find the ML. So for ML we have to take this size of this one, this point shifts here now. So now we have to take the length of this side divided length of total. Okay, in this case of if you have to find mass fraction of solid, that means we have to take length of this side divided length of total line. Okay, and this is the lever arc bone, right? Just when we solve some numerical examination, it will be applied frequently. Okay, right. Now we come over some important interesting point. What is some important conclusion of this copper nickel phase diagram? In copper nickel phase diagram, we have, because we have already discussed, we have already told that this copper nickel can be mixed completely solid and liquid phase. That means in liquid phase they are completely soluble, but in the solid phase also they are completely soluble. That means why in liquid phase it's soluble, this is understandable, okay, but in solid phase it's also completely soluble. That means copper and nickel mix with each other at atomic level. As a result of that, the single phase appears in solid phase. In liquid phase it appears in single phase. This is not a surprise, but in solid phase it appears in single phase. That means why? Because the copper and nickel mix with each other at atomic level. Solidification takes place over a range of temperature. At a certain range, the solidification takes place. Okay. Now this is mushy zone. We are coming over there now. This is the mushy zone. This is complete zone is called mushy zone. This mushy zone, since in this mushy zone there is this is a mixture of solid and liquid. So as the size of mushy zone increases, these properties will be varying. Okay, this is the third point. For larger mushy zone, the more will be variable of the properties of LOI. So as they increase the size of mushy zone, the variable of property of LOI will be increasing. So smaller mushy zone, less variable of property will be there. If size of mushy zone will be larger, the variable of property of LOI will also be increasing. Okay? If the LOI cools along the line as shown in phase diagram, because this line come over this diagram. This is the, as the temperature downs, this is very important observation here, be careful. As temperature downs, since at this point there will be temperature more than that of, suppose that at this point this temperature is 1600 degrees centigrade. As the temperature decreases, what will happen? The percentage of solid will be increasing. That means the percentage of solid will be increasing. That means percentage of solid, the mass fraction of solid will be increasing. Mass fraction, as temperature decreases, the percentage of solid will be increasing. In that condition, if percentage of solid will be increasing, that means percentage of mass fraction of solid will also be increasing. It might be observed here also, because as temperature drops, suppose that at this point we have to find, suppose that we have to find at this point mass fraction of solid. That means we have to take this AB by AC, but as temperature, let us suppose this point B shifts here. In that condition, this will be this size of this length by complete this one. So in that condition, this size, as the temperature drops, this length of side AB will be more. In that case, this length will be this one. But in previous one, at higher temperature, this length is this one. So as temperature this one, the length of AB will increase. Therefore, as the length of AB increases, in that condition, we are finding that mass fraction of solid will be increasing. Okay, this is the important point we have to understand, right? So if the alloy cool along the line as shown in phase diagram, as temperature decreases, percentage of nickel in solid phase increases. As temperature decreases, percentage of nickel in solid phase also decreases, right? And the mass fraction of solid increases. It is clear. As temperature drops, the percentage of liquid, percentage of solid will be increasing. In that condition, mass fraction of solid will also be increasing. This is the important thing we have to understand in copper nickel phase diagram. This was all about the copper nickel phase diagram. These are materials which are completely soluble in liquid as well as solid state. Since both can be mixed at atomic level, therefore both materials appears in single phase, in solid phase. Okay, so this is all about this type 1 phase diagram. These materials which are completely soluble in liquid as well as solid state. This is one of the best example is copper nickel at this phase diagram. This is all about the phase diagram of this one, copper nickel phase diagram. Thank you. We will meet in next session.